This machine costs $400 million. It takes 40 cargo containers, 20 trucks, and 3 Boeing 747s to ship. Every advanced chip on Earth, in your phone, your laptop, your car, AI data centers, is made with one of these, and the company that makes it almost didn't build it. In the year 2000, a small Dutch company called ASML made a decision that most of the industry thought was premature, maybe reckless. They bet everything on a technology called EUV. It took 19 years to pay off, and it changed the world. To understand why EUV mattered, you need one law of physics and one law of economics. To print a circuit onto silicon, you use light like a photographic stencil. The finer the detail you want, the shorter the wavelength you need. There's a hard limit. You cannot print features smaller than the wavelength of your light. By the late 1990s, the industry had squeezed down to 193 nanometers, and the features chip designers needed were getting smaller, fast. The economics part is related to Moore's law. Every 2 years, transistor density doubles. Chips get faster, cheaper, smaller. It had held for 35 years. Every piece of modern computing was built on the assumption it would keep holding. If the light source couldn't shrink anymore, Moore's law would end. So the question wasn't just technical, it was existential. The industry narrowed the candidates to 4. Twice a year, 200 of the world's best chip engineers gathered in Colorado Springs to debate which one would win. Every technology had a champion. On the third day, everyone voted. Hard X-ray had the most support, but its light source was the size of a particle accelerator. A soccer field of infrastructure for one factory machine. Ruled out, 3 remained. Ion beam was precise but slow. Throughput is everything in manufacturing. Electron beam had Bell Labs behind it, serious pedigree, serious momentum, and then EUV, extreme ultraviolet, 13.5 nanometers, 14 times shorter than what was in use. In theory, a generational leap. In practice, EUV is absorbed by almost everything. Air, glass, any conventional lens. The system would need near-perfect vacuum, mirrors polished to atomic smoothness, and generating EUV at manufacturing power levels? Nobody had done it. The most powerful option, the hardest, by a significant margin. ASML had been hedging, parallel programs into all 3 technologies. Ion beam with a partner in Vienna, electron beam with Bell Labs, EUV with Philips Research and Carl Zeiss. Hedging makes sense when you don't know the answer. It becomes unsustainable when you run out of money. Around the 2000, the hedging ended. They chose EUV, not because the problems were solved, because when they examined the physics clearly, EUV was the only technology with a credible path to the resolutions the industry would eventually need. The others had ceilings. EUV didn't. The direction was right. The road was unknown. ASML's first researcher, the man at the center of this decision, was asked years later how confident he'd been. Ignorance can be a blessing. Had I known what was ahead of me, I honestly don't know if I would have chosen it. What came next was 19 years of problems that didn't exist yet. In 2000, ASML believed EUV would reach volume production by 2006. It took 19 years. Every time they got close, the goalposts moved. Existing technology kept getting extended, engineers squeezing more life out of 193 nanometers than physics seemed to allow. Every extension pushed EUV to a smaller, harder node demanding more power, better optics, tighter tolerances. Power target, 40 watts, then 100, then 200. Every time they met the spec had moved. The hardest problem was the light source. Early machines used a discharge arc, a few watts, 1 wafer per hour. By the time they reached 10 watts, the industry needed 100. Abandoned. The solution, a high-powered laser fired at a single falling droplet of tin. Tin plasma generates more EUV per pulse than anything else, but tin is corrosive. slowly destroying the mirrors it illuminates. Managing tin debris inside a machine firing 50,000 pulses per second was engineering of absurd complexity. A company called Cyma ground through it for years, a breakthrough in laser pulse shaping. Efficiency jumped, power climbed past 100 watts, then 200. EUV entered high-volume manufacturing at the 7 nanometer node in 2019 at TSMC. Before EUV, chip makers were doing multi-patterning, exposing the same wafer 4, 5, 6 times with conventional light just to approximate what EUV achieves in one pass. EUV collapsed that complexity overnight, and it didn't stop there. 5 nanometers, 3 nanometers, 2 nanometers, and counting. The chips running today's AI models exist because of a decision made a quarter century ago by a small Dutch company. No alternative, no other supplier, fewer than 60 machines per year. The waiting list runs years. Those 200 experts in Colorado Springs thought they were choosing a technology for the next node. They were wrong. EUV didn't arrive at 70 nanometers, or 50, or even 14. It arrived at 7, solving a problem far harder than anyone in that room had imagined, and that's the part that matters. This wasn't a breakthrough. It was a commitment, repeated over and over again for 19 years to keep going when the timeline slipped, when the physics fought back, when the target moved. Every step, the same question, and every time the answer was yes. The most important machine in the world wasn't built because it was easy to imagine. It was built because they kept choosing not to stop.